Let us study about differentiability. Derivative has two meanings. Geometrical meaning is that derivative is slope of the tangent drawn to the curve at x is equal to a if it exists. Whereas the physical meaning is the instantaneous rate of change of function with respect to independent variable. To be differentiable or derivable at any point, first of all, the function has to be continuous at that point. In general, derivative has two meanings. Discontinuity implies non-differentiability, but continuity never implies differentiability. Even if a function is continuous, we can't say it will be differentiable. It is obvious from the graph we can't draw any tangent on the curve y is equal to fx at x is equal to a. Slopes are different for x is equal to a plus and x is equal to a minus. Fx is not differentiable at x is equal to a. Note that, like continuity, differentiability can also be observed from the graph. The function should be continuous and there should be no sharp turn on the curve. All the curvatures should be smooth. Is the function derivable at x is equal to a? Is the function derivable at x is equal to a? Is the function derivable at x is equal to a? Is the function derivable at x is equal to a? In the previous functions, function represented by graph 1 is differentiable. Functions represented by graph 2 and graph 4 are continuous but not differentiable. Function represented by graph 3 is neither continuous nor differentiable. State whether the following statements are true or false. Let us see the graphical representation of differentiability. The slope of MAB equals tan theta, which equals f of c plus h minus f of c divided by h. As b tends to a along the curve, that is, in limiting situation, the expression becomes limit h tending to 0 f of c plus h minus fc divided by h. It represents the slope of the tangent drawn to the curve at c, fc. On taking the limit, we get the derivative d by dx fx. Suppose f is a real function and c is a point in its domain. The derivative of f at c is defined by limit x tending to 0 f of c plus h minus f of c divided by h. Derivative of f at c is denoted by f dash c or d by dx f of x. The function defined by f dash c is equal to limit x tending to 0 f of x plus h minus f of x divided by h. Wherever the limit exists is defined to be the derivative of f. The derivative of f is denoted by f prime x or dfx by dx, or if y is equal to fx by dy by dx or y prime. The process of finding derivative of a function is called differentiation. We also use the phrase differentiate fx with respect to x to mean find f prime x. The following rules were established as a part of algebra of derivatives. First, u plus minus v prime equals u prime plus minus v prime. uv whole prime equals u prime v plus uv prime. This is the Leibniz or product rule. Third, u by v prime equals u prime v minus uv prime divided by v square, where v is not equal to 0, and this rule is also known as the quotient rule. The following table gives us a list of derivatives of certain standard function. For fx is equal to x to the power n, we have f prime x is equal to nx to the power n minus 1. Similarly, for fx is equal to sin x, we have f prime x is equal to cos x. For fx is equal to cos x, we have f prime x is equal to minus sin x, and for fx is equal to tan x, we have f prime x is equal to sec square x. If limit x tending to 0, f of c plus h minus f of c by h does not exist, we say that f is not differentiable at c. In other words, we say that a function f is differentiable at a point c in its domain if both limit h tending to 0 minus f of c plus h minus f of c by h and limit h tending to 0 plus f of c plus h minus f of c divided by h are finite and equal. A function is said to be differentiable in an interval a to b if it is differentiable at every point of a to b. As in case of continuity, at the endpoints a and b, we take the right hand limit and the left hand limit, which are nothing but left hand derivative and right hand derivative of the function at a and b respectively. Similarly, a function is differentiable in an interval a to b if it is differentiable at every point of a comma b. Theorem 3. If a function f is differentiable at a point c, then it is also continuous at that point. Let us have the proof. Since f is differentiable at c, we have limit x tending to c fx minus fc divided by x minus c equals f dash c. But for x is not equal to c, we have fx minus fc is equal to f of x minus f of c divided by x minus c whole multiplied by x minus c. Therefore, limit x tending to c fx minus fc equals limit x tending to c fx minus fc divided by x minus c whole multiplied by x minus c, or limit x tending to c fx minus limit x tending to c f of c equals limit x tending to c f of x minus f of c divided by x minus c whole multiplied by limit x tending to c x minus c. We have limit x tending to c f of x minus c divided by x minus c is equal to f dash c. Since limit x tending to c x minus c is equal to 0, we have limit x tending to c fx is equal to 0, or limit x tending to c fx is equal to limit x tending to c f of c. Hence, f is continuous at x is equal to c. Let us have a corollary. Every differentiable function is continuous. Indeed, we have seen that the function defined by fx is equal to modulus of x is a continuous function. Now, consider the left hand limit. Limit x tending to 0 minus f of 0 plus h minus f of 0 divided by h equals minus h divided by h, which equals minus 1. Now, from the right hand limit, we have limit x tending to 0 plus equals 1. Since the above left and right hand limits at 0 are not equal, hence limit x tending to 0 f of 0 plus h minus f of 0 divided by h does not exist, and hence f is not differentiable at 0. Thus, function f is not a differentiable function. Let us study derivatives of composite function. To study derivative of composite functions, we start with an illustrative example. Say we want to find the derivative of f where fx is equal to 2x plus 1 to the power 3. One way is to expand 2x plus 1 to the power 3 using binomial theorem and find the derivative as a polynomial function as illustrated below. dfx by dx is equal to d of 2x plus 1 whole cube by dx, which equals d by dx of 8x cube plus 12x square plus 6x plus 1 equals 24x cube plus 24x square plus 6, which equals 6 into 2x plus 1 whole square. Now observe that if fx is equal to log of x, where gx is equal to 2x plus 1 and hx is equal to x cube. Now put t is equal to gx is equal to 2x plus 1. Then f of x is equal to h of t is equal to t cube. Thus, df by dx equals 6 into 2x plus 1 whole square, which can be written as 3 into 2x plus 1 whole square into 2, which equals dh by dt into dt by dx. Let us study a theorem on chain rule. Let f be a real valued function which is a composite of two functions u and v, that is f is equal to v of u. Suppose t is equal to ux, and if both dt by dx and dv by dt exist, then we have df by dx equals dv by dt into dt by dx. Suppose f is a real valued function which is a composite of three functions u, v and w. That is, f is equal to w of u of v. If t is equal to vx and s is equal to ut, then df by dx is equal to d of wou by dt into dt by dx, which can be written as dw by ds into ds by dt into dt by dx.